the last lecture, we looked at how to do inference on a single population mean, as well as how to do inference on two dependent samples whenever the observations could be paired. In this lecture, we're looking to do inference on the difference between two means whenever we have two samples, but these samples are actually independent of one another. So consider this situation. We have an Uber driver, and this Uber driver collects data on his passengers regarding the distance driven and if the trip was for personal or for business reasons. We want to know if there's a significant difference in the average ride length for business and personal trips. So notice first of all that we are comparing quantitative data across two levels of a categorical variable. Our categorical variable is the type of trip, whether it was for business or personal reasons. The quantitative variable is the mileage, the length of the trip. However, notice also that we have two independent samples. The trip can only be for one of the two reasons. It can't be for both business and personal reasons, so each observation is going to fall into only one of the two categories. As a result, we're not able to take differences between our observations like we were with matched pairs. Now in one sample inference, what we did was we tested some hypothesized value against the sample to determine if that hypothesized value was plausible. Now in the two sample t-test, or the difference of two means t-test, what we have instead is a hypothesized difference, which is denoted by mu naught. Now, if we hypothesize that the population means that we're comparing are actually equal to one another, then we're going to set mu naught equal to 0. In this case, the null hypothesis is going to be that mu1 is equal to mu2, or alternatively, we could subtract mu2 over to the left-hand side and rewrite the null hypothesis as mu1 minus mu2 equal to 0. However, we may also hypothesize that one of our population means is larger than the other by some specific amount. What we can do then is we can set our null hypothesis to be mu1 minus mu2 equal to mu naught, where mu naught is some specific hypothesized difference that is not equal to 0. Now, to determine the alternative hypothesis, it's generally easiest to set up your null hypothesis first and then change the sign to the inequality that you want in order to get the desired relationship that you want to test. More formally, the two-sample t-test, or the difference of two means t-test, is used for comparing the means of two independent populations. We need 5 conditions to hold in order to run this test. Independence, randomization, and the 10% condition are the 3 conditions that you've seen quite frequently before. We also need the nearly normal condition, and in this case, we need to make sure that the distribution of both of our sample means are both approximately normal. The last condition that we need is the independent groups assumption. What we need here is for the groups that we're comparing to be independent of one another so that each observation falls into one and exactly one of our two groups. Now the test statistic is going to follow a t-distribution, and it's calculated by taking the difference between our two sample means, x1 bar minus x2 bar, subtracting off the hypothesized difference, which is commonly set equal to 0, and then dividing by the standard error, the square root of the sample variance of the first sample divided by its sample size, plus the sample variance of the second sample divided by its sample size. Now, notice that we have a very complicated formula for calculating out the degrees of freedom. You 100% do not need to know how to calculate out the degrees of freedom using this formula. As we'll see a little bit later on, Excel is going to be able to calculate out those degrees of freedom. You simply need to understand how to calculate out this test statistic. Now let's go back to our Uber driver. We want to know if there's a significant difference in the average ride length for business and personal trips. So in the null hypothesis, we can set up that the average length of a business trip is equal to the average length of a personal trip. Alternatively, we can subtract the average length of the personal trips over to the left-hand side to say that the difference between the two population means is equal to 0. Either way you write out the null hypothesis, what we're saying is that there's no difference in the average length of business and personal trips. Alternatively, notice that we're just asking if there's a significant difference in the average ride length. We don't have any kind of a hunch as to which one of the two might potentially be larger. So what we should do is hedge and use a two-sided alternative. We want to say in the alternative that mu sub b, the average ride length for a business trip, is not equal to the average ride length for a personal trip. Or again, another way of writing this is to say that the difference between the two means is not equal to 0. This alternative hypothesis is saying that the average length of the two trips are simply not equal to one another. One of them is significantly larger or smaller than the other. So this Uber driver goes out and collects data on his passengers' rides. Column A contains 25 observations for business rides. Column B contains the lengths of 15 personal rides. Columns E and F are calculating out our sample statistics. So notice that the business rides have a sample mean of 7.46 miles with a sample standard deviation of 5.05 miles, and we again have 25 observations. For the personal rides, the sample mean was only 5 miles with a sample standard deviation of 2.3 and a sample size of 15. In column F, notice that because we changed from the business to the personal rides, we also have to change the argument inside of the function whenever we go to calculate out the mean, standard deviation, and the count for the personal rides. We have to change from column A to column B. Now, looking at the histograms over on the right, what we see is that the length of the business trips histogram is slightly skewed to the right, and the histogram for the personal trips is very close to being normally distributed. Let's take a look at the conditions now. The observations that we have in our sample are certainly going to be independent of one another. One passenger's Uber trip is certainly not going to impact the length of another passenger's Uber trip. The observations are going to satisfy the randomization condition because passengers are randomly assigned to an Uber driver whenever they request a ride, so they make up a random sample out of all Uber rides. The 10% condition is certainly going to be satisfied because there's definitely more than 250 trips for business reasons and 150 trips for personal reasons. Taking a look back at our histograms on the previous slide, we can see that the nearly normal condition is going to hold for both of our samples. The business trips were slightly skewed to the right, but our sample size was between 15 and 30, which allows us to say that the central limit theorem holds. So we can say that the shape of the sampling distribution of x bar is approximately normal. As for the personal rides, the histogram was very close to being normal. In addition, we had 15 observations, so the central limit theorem is actually going to hold for two different reasons. In this case, the histogram is close to normal, and we have a reasonably large sample size. Finally, we definitely have independent groups because an Uber trip cannot be for both business and for personal reasons, is only going to fall into one of those two categories. Let's calculate out the test statistic now. We already know that the average ride length of a personal ride is 5 miles, and the average mileage on a business trip is 7.46 miles. We also know that the sample standard deviation for the personal trips is 2.3, and the sample standard deviation for the business trips is 5.05. We also have sample sizes of 25 for the business trips and 15 personal trips. So our test statistic is going to be the difference between our two sample means, 7.46 minus 5. We're also technically subtracting off a 0, which is our hypothesized difference. That's, of course, not going to change the value of our numerator. We're then going to divide that 2.46 in the numerator by the standard error, the square root of the sample variance of the business trips 5.05 squared divided by its sample size of 25 plus the sample variance for the personal trips 2.30 squared divided by its sample size of 15. This is then going to give us our test stat of 2.097. Just like we saw back in matched pairs, we're able to use the data analysis toolpack in order to run a two-sample t-test in Excel. Notice that our data is contained in columns A and B. What we're going to do is click on the Data Analysis Toolpack button, which will bring up the menu that you see at the top. What we want to do is select t-test two-sample assuming unequal variances. Now, notice there are actually two different options there for a t-test with two samples. We will cover the two-sample t-test assuming equal variances a little bit later on in this lecture. So choosing the one for unequal variances will bring up the box that you see down at the bottom. What we can do there is select our data. Variable 1 range is going to be everything involving the business trips. Variable 2 range is going to be everything involving the personal trips. Our hypothesized difference is going to be equal to 0. And because we have the category names in row 1, we want to check the box that says labels. Clicking OK will give us the output that you see over on the far right. So notice that we have one column for business and one column for personal, where we get the sample mean, the sample variance, and the number of observations. Row 7 contains our hypothesized mean difference. Row 8 contains our degrees of freedom. So this 36 that you see in cell B8 is the calculation of the degrees of freedom that you saw a little bit earlier that involved that really messy formula. Like I said, you don't need to calculate that out by hand. Excel is going to be able to do that for you. The t-statistic is 2.097, which matches what we calculated on the previous slide. And because we have a two-sided alternative, we want to use the two-tailed p-value, which is contained in row 12. That p-value is going to be 0.0431. So finishing off the mechanics, we can again just copy what we saw on the previous slide, 36 degrees of freedom from row 8, and a p-value of 0.0431 from row 12. Now in terms of our conclusion, we again don't have a set level of significance, so we assume 0.05 is going to be our level of significance. Comparing the p-value to alpha tells us that we are able to reject the null hypothesis because our p-value is less than 0.05, and we're able to conclude that the average length of Uber rides for business and personal reasons do have significantly different lengths. Now we started out with this two-sided alternative. We can go one step further and we can compare the sample means. After comparing the sample means, we can say that there is some kind of an indication that business trips are longer than personal trips because that sample mean was about 2.5 miles longer than the sample mean for the personal trips. Let's take a look at a different example. Suppose we have random samples of United States and United Kingdom high school students. Each of them is given a world map, and they're told to label as many countries correctly as they possibly can. What we want to do is we want to compare the average number of countries that students in the United States can name correctly and compare that to the average number of countries that a student from the United Kingdom can name correctly. Now, in order to make this comparison, what we can do is use a confidence interval for the difference between the two means. We can center the interval at the difference between our sample means. We can use the standard error to find the upper and the lower bounds for the difference. And then we can search for 0 inside this confidence interval. If 0 is contained within the confidence interval, then that's an indication that there is no significant difference because we'll have both positive and negative values in the confidence interval. That will tell us that either mean, the United States or the United Kingdom, could plausibly be larger. On the other hand, if the entire interval is positive, then the first mean that we used in the order of subtraction is significantly larger. And if the entire interval is negative, then the second mean in the order of subtraction is going to be significantly larger. So to estimate the difference between two population means, mu1 and mu2, using a confidence interval, we can center the interval at the difference between the sample means, x1 bar minus x2 bar. Then we'll add and subtract the margin of error, which is calculated by taking the critical value from the t-distribution times the standard error of the difference between the two means. The sample variance for the first sample divided by its sample size, plus the sample variance for the second sample divided by its sample size, that entire sum underneath the radical. Now, note a couple of things here. First of all, the assumptions and conditions for using the t-distribution are the exact same as the hypothesis test. And second of all, the degrees of freedom used in the confidence interval match the degrees of freedom in the hypothesis test. So again, you won't have to worry about calculating out that number. Excel is going to be able to calculate out the degrees of freedom for you. So let's start to check the conditions to make sure that we can actually use a confidence interval here. The independence condition is certainly satisfied because one student's knowledge of how to label countries correctly on a world map does not impact another student's knowledge unless they studied together. And it would be highly unlikely that if we're taking random samples from across these countries, that we would get two students from the exact same region who happen to also study together. The randomization condition is also going to be satisfied because the students are randomly selected, again, from all across these countries, meaning that we have representative samples of United States and United Kingdom high school students. If we take a look at the data, notice that we have 30 observations from the United States and 30 observations from the United Kingdom. This is important in determining if the 10% condition is satisfied and if the nearly normal condition is satisfied. Looking at the histograms down towards the bottom, notice that the histogram for the United States is slightly skewed to the right. It has the peak at around 16 countries labeled correctly, and it extends out to the right a little bit farther. As for the United Kingdom, the peak is right around 30, but this is a little bit more severely skewed to the right. Now, checking the 10% condition, we certainly have more than 300 students in the United States and in the United Kingdom, so our samples comprise less than 10% of the total number of students in both of our populations. Even though both of our histograms were skewed to the right, our sample sizes were at least 30 in both of our samples. So as a result, the third rule of thumb in the central limit theorem is going to hold, so we can guarantee that the shape of the sampling distribution of both of our sample means are both approximately normal. And we definitely have independent groups. There's no possible way that a student can be both from the United States and also taking classes in the United Kingdom. So there's absolutely no overlap among the students in our sample. Now, going back to our data, we can start to take a look at all of our sample statistics. Students in the United States were able to label, on average, about 17.3 countries correctly, with a sample standard deviation of 6.51. Students in the United Kingdom, on the other hand, were able to label about 32.5 countries correctly. However, they had a much larger sample standard deviation at 20.1. I used the equation for calculating degrees of freedom and set up a formula in Excel. Based on the values in that formula, we can see that there are 35 degrees of freedom in this test. The last thing that we're going to need to calculate is the critical value for our confidence interval. So taking a look at the t-table over on the right, we can match up the bottom row in the table, which has 35 degrees of freedom, with the column for 95% confidence, and see that our critical value for this confidence interval is going to be 2.03. So putting everything together, what we know is that the sample mean for the United States is 17.3, the sample mean for the United Kingdom is 32.53, the sample standard deviation for the United States is 6.51, and the sample standard deviation for the United Kingdom is 20.1. We know that we have 35 degrees of freedom, and whenever we go to set up our confidence interval, what we're going to do is center the interval at the difference between the two sample means, 17.3 minus 32.53. So we're going to do the United States minus the United Kingdom, plus and minus 2.03, which is our critical value, times the standard error, the square root of the sample variance for the United States, 6.51 squared divided by 30, plus the sample variance for the United Kingdom, 20.1 squared divided by 30. Notice that we could have also found the critical value by using the t.inverse.2t function in Excel. Because we want 95% confidence, we're leaving out 5% total, and we have 35 degrees of freedom. That function would have also given us our critical value of 2.03. Taking the difference between our sample means gives us negative 15.23. We have a margin of error of 7.831, which is going to give us a final confidence interval of negative 23.061 up to negative 7.399. Now, I also want to mention at this time that the order of subtraction that you choose for a confidence interval doesn't matter. You don't have any kind of a null hypothesis set up that's dictating the order of subtraction. So we very easily could have just done the United Kingdom minus the United States. So we would have had 32.53 minus 17.3. None of the values in the margin of error would have changed at all. So our final confidence interval would have been positive 7.399 up to positive 23.061. We would have gotten the exact same confidence interval if we had reversed the order of subtraction, but the signs on our bounds would have just taken on the opposite sign. Either way we do this, we're still going to come to the same conclusion in the end. So here's what we're able to deduce about the number of countries that students in the United States and the United Kingdom are able to name correctly. We can say that we're 95% confident that, on average, students in the United States can label between 7.399 and 23.061 fewer countries than students in the United Kingdom. And we're able to say this because we used the United States first in the order of subtraction, and the entire interval was negative. Now, because this confidence interval does not contain 0, there is a significant difference in the population means. And because the entire interval was negative and the United Kingdom was second in the order of subtraction, we can say that students in the United Kingdom appear to be able to name significantly more countries correctly compared to students in the United States. The two-sample t-test actually adjusts the degrees of freedom down because it makes this assumption that the variances of your populations are not equal to one another. That may not always be a reasonable assumption, though. We may have some information about the populations that give us the indication that the variances of these populations are actually equal to one another. And if that happens to be the case, and we can make this assumption that the variances or the spreads are the same, what we can do is we can pool the data in order to create a single estimate of the variance. This estimate is called the pooled variance. It's denoted by S sub p squared, and it's calculated by taking basically a weighted sum of your individual sample variances. We have the first sample size minus 1 times its corresponding sample variance, plus the second sample size minus 1 times its sample variance. We then divide that sum by the total number of observations altogether, n1 plus n2 minus 2, or alternatively, n1 minus 1 plus n2 minus 1. The rule of thumb that we tend to use in deciding if we're allowed to pool the variances is we take the ratio of the two sample variances. We put the larger sample variance on top, we put the smaller sample variance on the bottom, and if the ratio between the sample variances is less than 2, then those variances are close enough to say that they are approximately equal, so we can use this pooled estimate of the variance instead of using the separate variances. Now, the process for pooling your variances together and using this in your hypothesis test and your confidence interval is very similar to what we did earlier. The only difference is a slight change in the calculation of the test stat and the standard error in your confidence interval. The test statistic in the pooled t-test is going to have n1 plus n2 minus 2 degrees of freedom. It's still going to follow a t-distribution. The numerator is still the same, the difference between your sample means minus the hypothesized difference, and then we divide that by a little bit of a different standard error. Now what we have is the pooled standard deviation, the square root of what you saw on the previous slide, times the square root of 1 over n1 plus 1 over n2. The confidence interval, you should notice that there's a similar type of change. The interval is still centered at x1 bar minus x2 bar. We're still adding and subtracting the margin of error, but now the critical value in the calculation of the margin of error is again going to be a t-statistic with n1 plus n2 minus 2 degrees of freedom. Degrees of freedom are much easier to calculate here than in the original test. And then we multiply that critical value by, again, pooled standard deviation times the square root of 1 over n1 plus 1 over n2. The assumptions and conditions for this test are identical to what we did in the two-sample t-test, but we also need this additional equal variances assumption, which is that the variances of these populations are approximately equal to one another. So let's take a look at this example. We have random samples of people who have brown and blonde hair. Each one of them is given a pain tolerance test and receives a pain tolerance score on a scale from 0 to 100 based on how much pain they're able to tolerate. We want to know if people who have blonde hair have higher pain tolerances compared to people who have brown hair. So we can set up our null hypothesis so that the two means are equal to one another. The average pain tolerance score for the people with blonde hair is equal to the average pain tolerance score for people with brown hair. Or alternatively, we can subtract the mean for the people with brown hair over to the left-hand side and say that the difference between the two means is equal to 0. For the alternative hypothesis, we want to test to see if the average pain tolerance score for those with blonde hair is significantly greater than the average pain tolerance score for those with brown hair. Another way of writing our alternative would be again to subtract over the mean for the people with brown hair over to the left-hand side and say that the difference between the two is greater than 0. Let's take a quick look at the output right now because we actually need to find the sample variances in order to check the equivariance condition. In the output over on the right, we have our sample variances in row 5. The people with blonde hair have a sample variance of 87.43, and the variance of the people with the brown hair is 50.78. So what we need to do now is use these sample variances to check the equivariances assumption. We take the larger sample variance, 87.43, and divide it by the smaller sample variance, 50.78. It doesn't really matter what that value is. All that we really need to see is the fact that that number is less than 2. The larger sample variance is less than twice as large as the smaller sample variance. What this means is that the equivariance assumption is going to be satisfied, so we are going to be allowed to use the pooled variance or the pooled standard deviation in our calculation. For the sake of time, let's just also assume that the other 5 conditions are going to hold for this test. So let's take a look at the data here. Over on the left at the top, we have our pain tolerance scores. We have 10 observations for people with blonde hair, 9 observations for people who have brown hair. In the center, you see the 2 dialog boxes that you'll use in order to run the pooled t-test. If you click on the Data Analysis Toolpack button, this same menu will come up, and because we're making the assumption that our variances are equal to one another, we can choose the option t-test to sample assuming equal variances. That will then bring up the next dialog box, which you use in the exact same way as we did earlier with the generic 2-sample t-test. Select the data in column A and the data in column B, put in 0 as your hypothesized difference, and check the box for labels. Once you click OK, you'll then get the output that you see over on the right-hand side. Now, there's one additional statistic that you get in this output, which is in row 7. Row 7 contains the pooled variance. In this case, this is equal to 70.18. And this is the value that we're going to use in the test statistic instead of the individual variances. Notice down below that we also have our t-statistic. We have an upper one-sided test. So we're going to use the p-value that you see in row 11. We have a test statistic of 1.44, and that's going to correspond to a p-value of 0.0840. So putting everything together, we can take the pooled variance from row 7 on the output on the previous slide of 70.18 and take the square root of that to get our pooled standard deviation of 8.38. Calculating out the test statistic, we take the mean pain tolerance score for the people with blonde hair, 55.1, subtract off the mean pain tolerance score for the people with brown hair of 49.56, and then subtract off our hypothesized difference of 0. In the denominator, we take the pooled standard deviation of 8.38, multiply by the square root of 1 over 10 plus 1 over 9 to get our test statistic of 1.44, which matches what we saw on the previous slide. In terms of degrees of freedom, we take the sample size for the people with blonde hair, which was 10, add on the sample size for the people with brown hair, which was 9, subtract off 2, and get 17 degrees of freedom. And the p-value we can again just pull from the output, 0.0840. Now, if instead we wanted to calculate out a confidence interval for the difference between the mean pain tolerance scores, we already know that the sample mean pain tolerance score for the people with blonde hair is 55.1, the sample mean for the people with brown hair is 49.56, and the pooled standard deviation is 8.38. The critical value is going to be 2.11, and our confidence interval here is going to be calculated by taking the difference between our sample means, 55.1 minus 49.56, plus and minus our critical value of 2.11, times our standard error of 8.38 times the square root of 1 over 10 plus 1 over 9. This is going to give us a lower bound of negative 2.58 and an upper bound of 13.67. So finally, we can take a look at what the results of both the hypothesis test and confidence interval tell us. With a p-value of 0.0840, we're going to fail to reject the null and conclude that there is no significant difference in the pain tolerances of people who have blonde hair compared to those who have brown hair. Moreover, when we look at the 95% confidence interval, that is consistent with the decision in the hypothesis test. The confidence interval contains 0. It has both positive and negative values, which tells us that either one of our two population mean pain tolerance scores could plausibly be larger than the other.